Welcome back. Let's talk about capacitors and inductors. We'll start with capacitors. So here's a model of a capacitor, the diagram and the math. And physically, a capacitor is two plates that collect either charges or the lack thereof. That is, on one plate you're going to have electrons piling up, which are negatively charged, and on the other plate you're going to have holes or the lack of electrons piling up. And that's a simple explanation. The physics of these gets more involved, but as engineering, from an engineering perspective, that's what we're interested in, is just the basic behavior here. But there's a dielectric between here, so there's an insulator between there. And then physically, these plates are very large. There's a lot of surface area, and they typically roll these up in a jelly roll. Is a common way to construct these things. Okay, so we have a voltage across this thing and we have a current through it, and those have directions, and that's important because this math here, this equation that relates the current to the voltage it corresponds to this diagram here. So the voltage will kind of be opposite the current direction, all right? And the current voltage relation is given by this little equation here. The current is proportional to the change in voltage, right? The current I is given by the capacitance, which you can think of as a constant of proportionality, and then the V, the derivative of V. Okay, in fact, these things are manufactured to obey this math right here, right? Because we have this calculus and we know how to do all of these fancy things with calculus. So they've constructed these devices to obey that. And that's been how we've been able to develop and all of this stuff over the last couple of centuries. And I think it's important to point out that for a long time we were limited to these kinds of analytical calculus solutions. But now we have computers which are not limited to these kinds of solutions. Computers can handle a lot, much wider variety of math, and so that opens up a lot of possibilities for design, circuit design in the future. But this is a beginning level circuits class. We're just going to focus on the classic solutions. But I mention that because it is significant what's happening with the capabilities of computers and how that can change circuits. Anyway. So just sticking to classic calculus and classical circuit theory, because of this I equals CV prime, there's a couple of things that are most important. One is that the voltage cannot step change. That is, it can't jump from one level up to another, because the derivative would be infinite there. That would result in an infinite current, which can't happen. That's one way to think about it mathematically. The other way to think about it physically is that you're talking about a instantaneous change in the energy in this thing, and that's impossible. It takes time for energy to flow into a device, because yeah. All right, and the other thing that kind of follows from this calculus derivation here is that when the voltage is constant, the derivative will be zero. So the current will be zero, because C times any number times the zero is going to be zero. So when the voltage is constant, that is, the voltage across here is not changing, this guy behaves like an open circuit. All right, and kind of underlying this, what we've said is this other idea, in that there's this idea of displacement current. That is, all the current that enters this terminal and leaves this terminal, it comes from the device, or it stops at the device. That is, there's an insulator in here. Current cannot flow through this device. It either goes in and gets stored up, or it comes out. So that's kind of a weird thing. So we call the current in a capacitor, we sometimes refer to that as the displacement current, because it's kind of coming from in here. We'll talk more about that, but another way to think about what I'm saying here about the displacement current is that the capacitor is a storage device. It stores up energy. How much energy? Relatively speaking, not a super whole lot. Like, compare that to a battery. Capacitors have a very a very low amount of energy in joules compared to what a battery can store. And continuing on that line of logic, a quantity of gasoline has even more energy, and that's the problem that we're in our societies. We have so much energy available in gasoline that it's hard to say no to gas. It's because we like energy. I like energy. Everybody likes energy. All right. So just taking this guy right here, this I equals CV prime, and doing a little bit of math on it, we end up with these equations for the four quantities that we're most interested in this course: current, voltage, power, and energy. All right. So current is given by I equals CV prime, and once again, or I'm not sure I did say that these devices are manufactured to obey this rule right here, because we have these rules and we have all the hundreds of years of calculus and stuff that the mathematicians have been working on for centuries. We have all of that. We because of that we created these devices. That is, we fine-tuned the physical properties, how much foils are you using, and how tightly are you winding them, and what kind of dielectric, and the temperature properties, and all of these properties. We fine-tune them such that this guy behaves like this. And that's important to keep in mind, because it may be better. It's possible to make a device that might be better in some regard if you forsake this behavior, right? But we don't. Typically, we manufacture these guys to obey this calculus equation because we have all these math rules. But we're doing modeling here. We're building mathematical models. So we're sticking to this math. But keep in mind, once again, to repeat myself, it may be possible, or it may be desirable, to change the construction of a capacitor in such a way that you get some other property that you're interested in. Could be energy, could be energy storage, and if you did that, it may break this rule here. Okay, but keep that in mind. We're doing modeling, and we're going to stick to this rule because we can work problems like that. But in the real world, you got to know when to apply the classical models and when to vary from the classical models. That's a really super important skill. All right, back to the program. So we've got I equals CV prime. The capacitors are manufactured to obey that. And our calculus rules tell us that we can basically invert this equation by, taking the integral of V, and we can solve this guy for V. That's just calculus stuff. So we end up with V equals 1 over C integral over some time period, t0 to t. And because we're integrating over a time period, then we have to use a different variable for time here, because otherwise you get confused with the variable t and the limits of integration. This is a calculus thing. It's not really a circuits thing. So go back and review that in your calculus if it's been a while since you've seen that kind of thing. Anyway, V equals 1 over C integral over some time period t0 to t of I d tau. And once again, d tau is really time, but we're using a different variable. And then plus V at t0. So there might be an initial voltage in this device that you need to account for. All right, we'll work a couple problems like that. All right, and then we've been given already P equals IV, okay, and we have I here, and if we leave one of the V's alone, we have this. Basically just substitute this equation in here for I, and you end up with this. Power equals CV V prime, or CV dV dt if you prefer dV dt notation over V prime notation for the derivative. There's that, and there's another one. If we substitute this integral into here, we would get a big ugly thing that we're not going to use, but you would get that as well. Okay, and then here's the common energy one. If you there's a derivation for this that we're skipping on why this is true, but it is true. Okay, the energy in the cap is given by 1/2 CV squared, and once again we're skipping the derivation. All right, that's the basics, the physics of capacitors, and I sort of wandered off into how that relates to engineering and what's a model and what's not a model and all that good stuff. All right, let's talk about inductors. Okay, an inductor is a little coil of wire, and there's usually some kind of core of maybe iron or other nickel or molybdenum or something in here some kind of core that helps conduct the magnetic flux. So physically, there's a lot going on in here, right? Physically, there's a magnetic field that goes through the core, and remember, changes in a magnetic field induce a current, and the other way around, that is, changes in current induce a magnetic field, and there's a whole lot of magnetism stuff going on, but we're going to ignore all the magnetic effects for the most part because we're only interested in voltage, current, power, and energy in a first semester circuits class. Okay, later on you'll come back and look at the magnetism stuff, but right now we're just interested in what we call charge effects, or voltage, current, power, and energy in terms of charge and the movement of charge, which is current, and the energy of a charge, which is voltage. Okay, so we're ignoring the magnetic effects for the most part. So we have our little circuit diagram model, and we have the math that's associated with it, and these polarities are important. That is, the plus is at the arrow entry, and that's how this equation is referenced. That is, these polarities here. If you're going to use this math, then you need to have these polarities set up in your circuit. Okay, likewise for the capacitor. So this guy here develops a voltage that's proportional to the change in current. Okay, so that leads to two main effects, which you can understand in terms of calculus and derivatives. That first of all, the current cannot step change, because once again that would result in an infinite voltage, which is not physically realizable. Even getting close to infinite is bad. And the physical effect that will happen with that is that you'll get arcing, because if you have a current flowing through here and you remove the voltage, the current will continue to go. That is, if the voltage, so as voltage is here, and you try and step change the voltage down to say 0, the current will just keep on going, and you'll get an arc. So there's that. And the other effect on this is, the other effect of this math is that the voltage is 0 when the current is constant, because the derivative of a constant is 0. So basically a inductor behaves like a wire when the voltage is 0. It behaves like a short circuit or a wire when the voltage is 0. Okay, so those two things happen. All right, so once again, similarly to how we did with a capacitor, we can take our equation that governs voltage and current in an inductor, and once again, these devices are manufactured to obey this rule because we have the math, not because it's necessarily ideal in all circumstances for this thing to behave this way, but that's the way we manufacture them to behave. And then we just do some calculus on that stuff, and the inverse of this equation is this equation here, which relates current to voltage. And then we have this P equals IV, and with a substitution here, we can get power equals Li I prime. And then presented without evidence is this equation for energy, W equals 1/2 Li squared. So the derivation's in the text and other places. And that's inductors. That's the basic principles of inductors. Okay, so look, V equals Li prime and I equals CV prime. Let's see what that would look like with a capacitor and an inductor. There it is. So I equals CV prime. So let's take a voltage source and hook it up to a capacitor and look at the waveforms for these guys. What would they look like? So if you were given So here we're going to be given a voltage signal because we want to stick with this I equals CV thing, because this is only requires us to do a derivative. Okay, once again, if we're given a voltage, then all we need to do is take the derivative. So it's a little easier than the other way around. Derivatives are a little bit easier than integrals. Okay, so if you're given a voltage, and this is an arbitrary voltage signal, so look, this voltage source so far in the course has been a constant or DC voltage, but now this is a voltage signal that's changing over time. So it's imagine this being provided by some signal generator, some fancy, very fancy voltage supply that can adjust, that you can not only adjust the voltage, but you can generate a voltage that's changing over time, and you can generate any waveform that you want, like a computer-driven voltage signal generator kind of thing. Okay, so this guy here generates a signal that it ramps up in a straight line. So the equation for that would be 4t, just an arbitrary signal. And then it starts decaying exponentially, given by this equation here, 4e to the minus t minus 1. Okay, so it peaks out at 1 second. It peaks out at that would be 4 volts. Well, then, yeah, 4 volts. So what is current? It's just going to be the capacitance times the derivative of these two signals. So the capacitance is half a microfarad. So the derivative of 4t is just 4, right? The derivative of 4t is 4 times 0.5 is going to give you 2. So I is 2, and this is going to be microamps because of the microfarad in there. Okay, so basically the derivative of this line times the capacitance gives you this line. Okay, and that's easy because it's a straight line and the derivative is easy to take. Now this one here, the derivative is a little bit harder, but not too hard. See if I can do it. The derivative of 4e to the minus t minus 1 is minus 4e to the minus t minus 1. And then you multiply that times a half, and you get minus 2e to the minus t minus 1. So basically this thing here, the derivative of this curve times half a microfarad gives you this current in microamps. So we're just applying this I equals CV prime, and notice that it flips direction here, and so which you would expect, because here the voltage is changing at a constant rate. The derivative is a constant, so the current is a constant. And this guy is putting out a current that agrees with the voltage change. It's going this way, it's going to the right, and going to the right more. It's increasing as the voltage increases. Okay, then as the voltage decreases, as the voltage starts decreasing, the current flips direction. The current immediately starts going the opposite direction. Just instantaneously goes the opposite direction, and then it starts slowing down. So it's first it's going this way, then it flips direction and then decreases its magnitude down to 0. So current can flip direction instantly in a cap, but the voltage can't step. See here the voltage is it's not stepping, it's just it's getting bigger up to a point, and then it starts getting smaller, but it's not dropping by some quantity. Okay, that can't happen. That cannot happen in a cap. You cannot have a step change in a cap. Okay, otherwise you'd get an infinite voltage. Okay, so you cannot have a step change in the voltage in the cap, but you can have a step change in the current in the cap. So keep this concept straight. This is important. All right. Okay, so let's keep going. So P equals IV, right? Anybody ever heard that? So if we multiply these two curves together, we should be able to get a curve for current. So that's what's happening right here. P equals IV. Just multiply these two curves together, and you get this. You get 8T, right? Because 2 times 4T is 8T. So the power is increasing at a steady rate, let's say. Let's use that language to describe this thing. It's increasing at a steady rate. And remember, power is something that flows. It's the flow of energy, right? It has time in it. Okay, it's joules per second. So the energy is flowing into this device, and then as the current flips direction, the energy starts flowing out. So here it's flowing in, and then it immediately, as the voltage starts decreasing, the current immediately changes direction. Likewise, the power immediately changes direction. The power was initially flowing into this device, and now it's flowing out. It's flowing in. Oh, I'll stop there. Don't want to wander off too much about the nature of this power flow, but maybe later. Yeah, so it's flowing into the device, and then it's flowing out of the device. And then lastly, the energy. Now the energy is the energy stored in the cap. So it's going to come up, and as it's coming into the cap, so there's all this energy. There's four, I'm not sure if this is micro or nano or whatever, but it's 4 something joules. And then it starts coming out. So the power can flip direction, because here it's flowing in, and then it immediately starts flowing out. But this is the total energy that's in the device, and it couldn't just all leave at once, right? So this isn't going to go negative. There's no such thing as negative energy anyway. But it's not going to have a step change. It's not going to have a step change, which relates to the V not being able to have a step change, right? Because energy is 1/2 CV squared. So if the voltage can't step change, then the current, or the voltage cannot step change, then the current's not going to be able to step change likewise, because it has a V term in it. All right, so this is just the basics of voltage, current, power, and energy in a cap. This is a really good chart to just help you internalize the classical physics, classical calculus based behavior of a capacitor. Alrighty, let's talk about an inductor, and it's just going to be all of this stuff but flipped around. So I won't go into it in quite so much detail. But here you got your little inductor guy, and I've got a current source, and then I've got the inductor, and we're going to have the current source given because we just want to do a derivative. We don't want to. We want to try and avoid integration, because integration is hard. So we're given this arbitrary signal that changes with time. I goes up to some peak and then decays down, given by this thing, 10t to the, or 10t times e to the minus 5t. So when time is small, this guy is going to be dominated by the 10t part of the equation. So it's going to look like a straight line, mostly. And then as time gets bigger, the e to the minus 5t thing is gonna dominate, and it's gonna start coming down like an exponential decay. So it looks like this. I happened to solve this just because I was curious, and I wanted to know it has a peak at some value. I'm not sure, did I solve for the time? I didn't, but at some time it'll peak out at 0.776. It's not that important, but I did solve for that. So if you take the derivative of this guy and multiply times the inductance, right? If you take the derivative of the current and multiply times inductance, you get this thing. So we can use our classical understanding of calculus to help us kind of understand this and kind of pair that with the behavior of an inductor, let's talk about that. So on this part of the curve, the slope is positive. So the derivative is positive. So V will be positive. But the slope is decreasing over time, right? It's decreasing. So the voltage is decreasing, but it's still positive. At this point, at the maximum, the derivative is 0. So the voltage is 0, right? And then the voltage is, the current is, the slope of the current is negative. So the voltage is negative. Then the slope is negative and getting more negative until it reaches this inflection point where it starts getting bigger. It starts becoming bigger at this inflection point right here, right? So the voltage will go negative here and get more negative, and then reach a maximum negativity, and then start to become less negative, and eventually it'll go to 0. So that's the calculus way of understanding this, and the physical way of understanding this is that when the current is not changing, the voltage is constant, 0. It's for that instant in time. It's yeah, never mind that. And then that's about it. Okay. If you multiply these two curves together, you get this. A positive times a positive is a positive, and a positive times a negative is a negative. So the power is flowing in, more and more and more power. This is the maximum rate of power transfer here. This is maximum power transfer. Then the rate of power flowing in gets smaller and smaller. Now at this point there's no power flowing in. Then the power starts flowing out. And this is maximum negative power transfer, or the maximum amount of power that's leaving the device. Power is stored in this inductor. Inductors are energy storage devices. Not very much energy, but a little bit. Okay, and then the energy keeps leaving until it goes to 0. The power is leaving. Got to be careful with the terms power and energy. They're different but very closely related. So here's energy. So remember, power is the rate of change of energy. So you have energy flowing in and then energy flowing out. This is the total energy that's in the device, and it goes up to a maximum and then leaves. The energy the energy in the device will never be negative, mathematically, because this is squared. And physically speaking, there's no such thing as negative energy in the classical universe. Maybe in weirdo, quantum physics there might be, but we're just doing classical physics stuff. Let's see. That's about it. So study these and get comfortable with these relationships. This is fundamental to understanding how capacitors work, and that's fundamental to circuits, to understanding circuits. Okay, moving right along, we're going to have resistors and capacitors arranged in parallel and series, and we can simplify those. Similar to how we simplified resistors. So for inductors, it's actually exactly like a resistor in the simplification rules, because, well, physically for the same reasons. Like a resistor is just a length of material that has a certain resistance. If you want more resistance, you just use a longer length of that material. Same thing with an inductor. An inductor is just a coil of wire of a certain length. If you want more inductance, you just make the coil longer. So adding, two inductors in series, you can just add them. Okay, it's analogous to how a resistor works. And likewise, the parallel simplification is the same as for a resistor. You have the same mathematical rule as we saw for resistors. Okay, capacitors, that's all flipped upside down. So it's easiest to start with the parallel simplification, which is easier to understand conceptually. Now, conceptually, a capacitor is just two plates with a certain amount of area. They're just two plates close together with a dielectric insulator. If you want more capacitance, you just make the plate bigger, right? So if you have two capacitors in parallel, it's just like you just made a bigger plate, you know. So when they're in parallel, you can just add them, and then it also works out that the opposite, that is, capacitors in series, turns out that this rule applies. Now, it may not be as intuitively obvious as this is, but it is true. So just to summarize, when you're simplifying inductors, you just use the resistance rules. And when you're simplifying capacitors, you just flip those rules around for series and parallel. All right, that's that. The last thing is mutual inductance. So if you have two coils in close proximity, there are magnetic effects, right? We like to ignore the magnetic effects in introductory circuits class, but there are magnetic effects. There's a, what is it, the right-hand rule? The current's going this way. You've got the magnetic field going along your fingers. There's all that stuff going on. So there's magnetic fields going around this. So the magnetic field generated by one inductor is going to permeate the other inductor and induce a current, and vice versa. Okay, that's the basic idea of mutual inductance. But we've simplified it down to voltage, current, power, energy. Okay, we've abstracted out the magnetism part so that we can just deal with voltage, current, power, and energy. And later on in advanced courses, they'll tie the two together. They'll tie the magnetism back together with the charge. But we're just talking about charge effects. Okay, so first of all, look, point of confusion on this stuff. There's voltage and there's energy, and we can really separate the two discussions. There's going to be dots involved with voltage, and there's going to be dots involved with energy, but they're two separate things. First of all, the voltage rules. So here it is. This is the model. Oh, before we talk about mutual inductance, just as a review, really, we've already seen self-inductance. The self-inductance was the stuff we talked about with just the basic definition of an inductor. Way back in here, in we're really talking about self-inductance in the introductory material on how an inductor works. That's self-inductance. So I'm just reviewing that here. So one inductor will induce a voltage in itself. That is, the current flow in one inductor will induce a voltage in that same inductor. That's self-inductance. That's just regular inductor behavior. But if you have two inductors, then you get mutual inductance, right? So we're going to write equations that have self-inductance and mutual inductance. You got to keep them straight. Okay, so both effects will be present. The self-inductance effects will be there, and then if you have two inductors, there might be, depending if they're close together or not. You know, if the two inductors are close together, then there could be a mutual inductance effect, and this is the model for that. So just as self-inductance is given by V equals Li prime, where L is the inductance of a single a single inductor, we have this equation, V equals Mi prime, where M is the mutual inductance. It's the inductance from one device to another device. So in here, if you have a current in one inductor, it will induce a voltage in another inductor, and vice versa. But I'm only showing one side of that right now. Like this inductor, the current in this inductor is inducing a voltage in this guy over here. But the opposite will be happening as well. That is, there'll be a current in here, and it'll induce a voltage back in here. All right, and then they have polarities, and that's where these dots come into play, because the dots provide just another variable, really, and it has to do with how the coils are arranged relative to each other, because you can put inductors, you can wind them clockwise, you can wind them counterclockwise, and then you can vary the arrangement of those windings next to each other. That's basically what the dot means. And we're not going to go into the details of how the dots relate to the physical arrangement of these two inductors, but that's where it comes from. And for us, for our modeling, we just need to apply the dot convention correctly. So if the current, so here's the dot convention for voltage. We're just talking about the dot convention for voltage, not for energy, but for voltage. Okay, the dot convention is if the current comes into the dot, then the positive sign will be at the dot. And if it's otherwise, it'll be well. Another way to say that is if the current well, there's 4 cases, but if you just understand this one case, you can pretty much figure out the other cases. So there's also another case where if the current is leaving the dot, then the voltage will be leaving the dot. So I consider these to be agree. That is, they're both kind of agreeing with each other, but there's 2 other cases. Let's see, you could have the current leaving the dot. Ooh, wait, that's not current leaving the dot. Actually I'm confusing myself here. Let me see if I can start over here. So if the current is leaving the dot, the voltage will be at the dot. That's it, right? There's only one other case. It's either entering the dot or it's not entering the dot. Yeah. So here it's entering the dot. Let's see if it's not entering the dot. So here, in other words, leaving the dot. So here's the current is leaving the dot. So in that case, the positive sign will be away from the dot. Yeah. And it's still away from the dot. I could move this dot over here, and then I would put the positive over there. Basically, if it's entering the dot, the positive sign will be at the dot. Otherwise, if it's leaving the dot, the positive sign will be away from the dot. There's really only those 2 cases. It's not as bad as it might seem. We'll look at some problems in a bit. Okay, so what we did here was the voltage rules for mutual inductance, and I presented self-inductance really as a review. We always have self-inductance. An inductor, by definition, will have this self-inductance. That's what inductors do. Now, the mutual inductance happens when you have 2 inductors that are close together. So they have to be physically close together. And here, I've drawn them apart just so that I can squeeze in the positive and negative signs of stuff. But in reality, they're physically together. And the dots represent the coil arrangements. Okay, this is for voltage. This is the dot convention for voltage. We also have energy, and we have a dot convention for energy. So this is the one that there's 4 cases on. Yeah, I was confusing myself. Sorry about that. Anyway, so we've got the mutual inductance M, or sometimes called the coupling coefficient. It's given by this. It's just the root of the individual inductances L1 and L2 times this constant K, where K is a value between 0 and 1. So this is just presented without derivation. Just learn to love it. And then the total energy of this coupled system. So you have two inductors that are coupled together in close proximity. the total energy in the device is going to be the energy in one and the energy in another one modified by this third term. So it's not additional energy in here, it's just sort of a modifier that modifies the sum of the energy. That's why this is presented all together in one equation. So you've got W, the total energy in the coupled system, this is just the energy in the first guy, right? That's our energy equation for an inductor, 1/2 Li squared. And this is the energy in the second inductor, 1/2 Li squared, with 2 subscripts, and here 1 subscript. Okay, so the energy in the first inductor plus the energy in the second inductor modified by this third term, M, I1, I2. And it's going to be either plus or minus. And the way I remember it is if the currents agree, then it's positive. And if the currents disagree, it's negative. So there's really 4 cases, but I just draw 2. And it's enough for me to remember. So here I have both currents entering the dot. I say that they agree, so it's positive. Here you have one current entering a dot, another current leaving a dot. I say they disagree. Strictly speaking, there's 2 more cases. They could both be leaving, which would look like what? They could both be leaving, but they still agree, so it would be plus. Or the other case is here I have one leaving and one entering and one leaving. I could have one leaving and one entering. It's it's the same. As far as remembering what to do with the sign, it's the same. Okay, so if they agree, if the current directions agree with the dots, it's plus, and if they disagree with the dots, minus. And it just modifies the total energy. Okay, so don't confuse the voltage dot rules with the energy dot rules. They're two different things. Keep in mind there's self, there's mutual. All right, I hope that was helpful. We'll work a whole bunch of problems next. Okay, see you next time. Bye.